So here's an example. Suppose you start at the corner of a room and walk 10 feet at an angle of 70 degrees to one of the walls. So let's draw that in. So from the corner of the room, we're going 10 feet at an angle of 70 degrees. We'll say that's 10 feet. Okay? So 10 feet and 70 degrees. Now, the next thing we do when we get to the end of that walk, we turn 80 degrees clockwise and walk another 7 feet. So if we consider that this is going to continue out 70 degrees, but we're going to turn and walk 7 feet 80 degrees off of there. So 80 degrees looks like it would be about there. And walk 7 feet. So what that means is we have walked 7 feet and this is 80 degrees. What we want to know is if we had walked straight from the corner to our stopping point. So from here directly to here, what would be the angle and the distance? So we're looking for this distance and this angle right in here. Well, with these pieces of information, we can see we formed a triangle, and we have information about two of the sides so far. We've got the 10-foot side and the 7-foot side, and we're looking for that third side. To solve, we're going to need a third piece of information, and it looks like we can get that interior angle between the 10-foot and 7-foot. If we look at what we've drawn, we can see that this interior angle is going to be 100 degrees, which gives me an SAS triangle to solve. Well, with an SAS triangle, we can't really use the law of sines because we don't have an angle with its opposite side in any form with the SAS triangle. So we're going to use the law of cosines and set it up. So I'm going to call this distance d. And we're going to solve for d with the law of sines. So d squared equals 10 squared plus 7 squared minus 2 times 10 times 7 times the cosine of 100. With the appropriate calculations, we'll find out that d is approximately equal to 13.1647. Now we have to solve for the direction angle for d. Now, the angle that we can solve for originally here would be this angle inside the triangle. And if we use either the law of sines or the law of cosines now, we can solve for that. Let's set it up. We would say that the sine of the red angle, let's just call that A, over 7 would equal the sine of 100 over D. Now if we solve for that angle, solving for angle A should give us a measurement of 31.5772 degrees. But that's not the angle that describes the direction for the vector D. What we're really looking for here is the angle here, which we can see is 70 minus angle A. So the angle or direction for D is going to be, we'll call that theta, 70 minus 31.5772, which is equal to 38 9.4228 degrees. Here's another example. We have a ship near the coast going 9 knots at an angle of 130 degrees to a current of 4 knots, where a knot is a nautical mile per hour, slightly more than a regular mile per hour. What is the ship's resultant velocity with respect to the current? All right, first of all, we see this word resultant, which tells us we're looking for the sum of these two pieces of information. Now we have to visualize what the situation is. So we start with this current of 4 knots, and we can pick that direction of the current to be whatever we want. So let's just pick a nice horizontal 4-knot current. And there it is. Now, we have this ship going 9 knots at an angle of 130 degrees to a current of 4 knots. So we will say that we've got this 9-knot current at an angle of 130 degrees. And here's our 4-knot current and our 9-knot current. Now what we're interested in is the ship's resultant velocity. We've got these two types of motion being combined. But what we've got here is actually two vectors that are connected tail to tail. So we're not really adding these two vectors. We want to be able to add these two vectors. So what I'm going to do is I'm going to translate one of the vectors so that they are connected head to tail. So I'm going to translate this by duplicating it. And now we're going to move it and connect it up here. So now our connection is head to tail. So our resultant vector then would be from where we started at the beginning of the 9-knot vector to where we end. So that's what we're looking for, the direction and length of that resultant vector. Now, we know that this is 4, and we know that that particular vector was 130 degrees. If we extended this vector down, we could see that this vector would be 50 degrees. So this would also be 50 degrees up here. And now I'm in that same SAS situation, which means the law of cosines is going to come in handy one more time. Now, we set it up so that our unknown value x squared equals 9 squared plus 4 squared minus 2 times 9 times 4 times the cosine of 50. Solving for x, we find that x is 7.122 knots. That allows us to find this interior angle once again as part of the triangle by using the law of sines. So let's call that a again. So sine a over 4 equals sine 50 over x, or 7.122. Those calculations allow me to find angle A, which turns out to be 25.484 degrees. If angle A is 25.584, we're looking for angle theta, the direction angle for our resultant vector. So that's going to be 130 minus 25.484, which turns out to be 104.516 degrees. So there we have our resultant velocity with respect to the current.